So in figure 10.1, it shows the same situation that we analyzed in example 9.7. So again, we're talking about a cable that's wrapped several times around the uniform solid cylinder with a diameter of 0.12 meters. So we can start writing some values. We know that the diameter, 0.12 meters, is a given, and we know that the radius is half of that, so the radius should be 0.06 meters. And then the mass that is given is 50 kilograms. Okay, so this uniform solid cylinder can rotate freely about its axis. The cable is being pulled by a force with a magnitude of 9.0 newtons. So we know that the force is 9 newtons. So we're being asked to find the magnitude of the acceleration of the cable if it unwinds. So let's try to draw this problem out first. We have here the uniform solid cylinder, the cylinder, and then we know that the radius is 0.06, so that's this value, and then the diameter is 0.12 meters, and then the force that is going in the left direction is 9 newtons. And then a cable is being pulled in that direction, so we can just imagine the cable going that way. And then the whole mass of this uniform solid cylinder is the 50 kilograms. So that is the main thing. And then we also do have the weight of the mass times gravity going downward, the weight. And we could probably find this with this. So the first thing we're going to do is try to find the torque. So the torque in this case, as we've used before, is the force times the length that we're finding. So the force, we know that it's 9 newtons, and then in this case the radius is 0.06. Because the radius is 0.06, and the mass is equal to this, so we can utilize this in our formula. So 0.06 meters, and then that brings us to 0.54 newtons times meters. Now we're going to try to find the inertia. The equation for the inertia is half of the mass times the radius squared. So we do know the mass in this case, so it would be half of the 50 kilograms times the radius that we also know, 0.06 squared. And that would leave us at 0.09 kilograms per meter squared. So this is the inertia. And then we actually can utilize the inertia to find the magnitude of the acceleration, which is the overall solution we're trying to get to. So now that we know both the values, we know that the torque is 0.54 newtons times meters, and we also know now that the inertia is 0.09 kilograms per meter squared. So now that we know this, we actually can find the angular acceleration that we're trying to get to. So the angular acceleration is the torque over the inertia. So we would put the 0.54 newtons per meters times meters, over the 0.09 kilograms times meter squared. And after we divide this, it gives us these two values end up in radians. We get 6.0 radians per second squared. And this is the acceleration that we've been trying to reach. So this is our angular acceleration. So now, if we do want to keep going to find the angular acceleration in more colloquial terms in meters per second squared, which is the normal amount, we can also use these 6.0 radians that we also know. So the acceleration in regular terms would be the radius times the angular acceleration. So we do have both of these values. We put the 0.06 again, times the 6.0 radians per second squared that we found, and it's 0.06 meters here. So we drop the radians because they're not a realistic value in these cases. So we would end up with a 0.36 meters per second squared. And that's the magnitude of the acceleration of the winch.